Have you ever stopped, I never really stopped to question what the universe is actually made of? We talk about particles, planets, galaxies,
Right.
things moving around. But what if? What if the core idea is wrong? What if everything, absolutely everything, isn't things in motion, but it is motion itself? Like the reality is the dance, the vibration, forget things that move. What if motion is the thing? Today, we're diving deep into this really wild idea from a thinker named Dewey B. Larson. He basically said the universe is nothing but motion. That was his whole system. So our mission here is to explore Larson's reciprocal system, or as he called it, his attempt to build all of physics from just motion. We want to see, okay, what did he get right? Where did it fall short? And how does this connect to a modern idea, motion theory, or MT? It's a journey into rethinking reality. Might shake things up a bit.
It's definitely a bold departure, yeah. It really forces you to shift how you think about everything.
Yeah.
Larson's core idea, his postulate, was stark. The physical universe, it's just motion.
Yeah.
Distributed in space and time, nothing else. He wasn't saying, particles or fields get motion later on. No. He argued the universe is motion, fundamentally.
Okay, let's unpack this a bit. If motion is all there is, how does that even work? Where does it happen? Larson saw space and time, not like
a stage, right?
but as interwoven aspects of the motion itself. And he had this key concept, natural progression. What exactly did he mean by that?
Right. Natural progression. It's basically a built-in default outward expansion. Think of it like the universe's default setting is expand outwards at what he called unit speed. This progression defines the scale of everything unless something specifically, constrains it or holds it back. So the universe isn't being pushed out.
Okay.
It's outward just by default. That's a really radical flip, isn't it? Expansion is just inherent.
That is pretty mind-bending. So if everything is just this motion, how do we get stuff, like actual things, a rock, light? What kind of motion builds the world we see?
Yeah, that's the fascinating part. In his system structure, like a rock or anything else, it's just motion that's kind of trapped in a pattern.
Yeah.
So, for example, tiny oscillations, like little contained wiggles in this motion, that's what we see as photons, light particles. Then, if the motion has rotational parts, sort of spinning components, that gives rise to what we call mass.
Okay, rotation equals mass.
In his view, yeah.
Yeah.
And combinations of these rotations and oscillations, they build up into atoms, molecules, everything bigger. He even saw gravity and the universe expanding as just two sides of the same coin, this natural progression. Gravity is like a local counterflow, pulling things together because of the mass, the rotation. But globally, that outward push, the progression, wins out. His big slogan, you said it, was always nothing but motion.
Right. Here's where it gets really interesting for me. How does he actually build a whole world, all of physics we know, from just motion? And he started treating motion as scalar, right? Just magnitude, no direction initially, like speed, not velocity. How did direction and, geometry, shapes, how did that stuff emerge?
Exactly. He said direction and geometry aren't fundamental. They emerge when these basic scalar motions combine and interact. And this connects to his idea of reciprocity. It's the notion that space and time can sort of trade roles, depending on the motion state. This swap defines his material sector. That's our everyday world, where space seems more dominant, and a cosmic sector where the roles flip and time is more dominant. It was his way to get cosmic effects without inventing new forces or particles. And that natural progression we talked about, super key. It's the default outward drift. Larson saw that as the reason for redshift light from distant galaxies stretching out and the overall expansion of the cosmos. Gravitation then is like a local countercurrent. It comes from those rotational bits, the mass, and it stabilizes things, holds structures together against that default outward flow, like an eddy in a river.
So the universe is this fundamental motion, and specific patterns, specific types of motion give us things, photons or oscillations. Matter comes from rotation, his spin on inertia and mass. Atoms are just complex clusters of these rotations, and chemistry is how they fit together. Wow. That's incredibly ambitious, trying to get everything, spectra, atoms, the whole universe from one single idea, using this two-sector thing to handle the cosmic stuff.
It really is. The ambition is kind of staggering. One postulate, all phenomena. He really went for it. Said, let's just see how far this one idea takes us. But, trying to explain everything from one starting point, it sounds almost too neat, doesn't it?
Yeah.
You have to wonder where a grand vision like that would inevitably hit some walls, even if parts of it were really insightful.
That's the perfect question, and it leads us right to, okay, what does this mean now? Because even with its limits, some of Larson's ideas were weirdly ahead of their time, and they really resonate with this modern framework, motion theory.
Yeah, what's striking is that motion-first ontology. Larson just starting with motion, not things.
Yeah.
That's spot on for motion theory, too. Both RS, his system, and MT, motion theory, see structure as fundamentally sustained motion
Mm.
and measurement itself. They both see it as synchronization with that motion. It's less about observing a static thing and more about tuning into its rhythm, its dynamics.
Like understanding music by listening to the performance, not just staring at the sheet music.
Exactly. And that extends to time as well. In both views, time isn't some external river flowing along. It's more of a relation between motions, a relative rate. MT adds a bit more detail here, saying clock rate equals sync rate. So how we measure time, our clocks, it's directly tied to the coherence, the synchronization of these underlying motions. Stable oscillations are what make clocks tick.
Okay, and this idea of structure by constraint, that seems like another big overlap. Larson had oscillations and rotations constrained, giving us photons and mass. How does MT handle that?
It's very similar conceptually. MT talks about coherence gates. These are like filters that select which patterns of motion, which rhythms are stable enough to actually persist. These gates are shaped by things MT calls sink pressure gradients and leak rates. You can kind of think of that as the stickiness or resistance in the motion field. Only the really coherent, stable patterns survive. The rest just dissolves. And Larson's instinct about large-scale expansion, explaining it without needing extra sort of metaphysical baggage, RS just saw redshift as a kinematic effect, part of the motion itself. Now, MT does keep general relativity, space-time curvature, and the standard Hubble expansion, but it really values Larson's drive for minimal ontologies. Try the simplest explanation first before you start inventing dark stuff to fill the gaps.
Okay, but let's get critical now. Because for all the brilliance, there were definitely challenges. Where did Larson's system really struggle compared to how modern physics handles things? That scalar motion thing feels like a big one.
You nailed it. That's the core problem. Scalar-only start versus vector tensor reality. Physics today is deeply directional. We use gauge fields for forces, spin for particles, curvature for gravity. These things have direction built in. RS really struggled to get that precision, that directionality, out of just scalar motion. His derivations often didn't match the quantitative success of Maxwell's equations or Dirac's or Einstein's. Motion theory takes a different path. It doesn't throw out that successful vector tensor math. Instead, MT reinterprets it as the language, the grammar, describing the structured motion. It's not new stuff, it's how the motion behaves.
Right, the description, not the substance.
Precisely. And that ties into predictive precision. Larson's claims about nuclear structure or the particle zoo or fine spectral details, they were often more qualitative, sometimes felt a bit like explaining things after the fact, post hoc. Contrast that with, say, PUED or the standard model. They give you numbers, predictions tested to incredible accuracy, like 10 decimal places sometimes. MT holds itself to that standard. As we sometimes say, if it doesn't predict a number that survives blinding, it's a poem. It needs to be testable. So if the universe is so directional and he started scalar, how did he try to bridge that? Did he just sort of assert it? And what about his specific model of redshift without expansion? Where did that fall down empirically? Well, his attempts to derive the directional stuff often, frankly, lack the mathematical rigor needed for real predictive power in the modern sense. And yeah, cosmologically, his model hit serious snags. Things like supernova distances, how bright they appear versus how far they are, or the tiny temperature fluctuations in the cosmic microwave background, the CMB anisotropies, and also baryon acoustic oscillations, these large-scale patterns in how galaxies are distributed, and maps of gravitational lensing, how mass bends light. All these observations are explained incredibly well by the standard ΛCDM model, the one with dark energy and dark matter.
The current champion.
Right. So MT doesn't discard those wins. It tries to find coherence-based explanations or refinements within that successful GR-λCDM framework, rather than starting over from scratch cosmologically. And that relates to the difference between derivations versus declarations. Larson's writing could sometimes just assert things, like mass is rotational motion, period, without maybe showing the full mathematical steps, the underlying action or invariant that reproduces known physics in the right limits. MT insists on finding that action for motion, a mathematical recipe that shows how motion behaves, and importantly, demonstrably reduces to GR, Maxwell, Schrodinger, etc., where they apply. That's how you connect to established physics and find testable consequences, like conservation laws via Noether's theorem.
That rigor seems key. Okay, so how does motion theory actually take Larson's core insight, nothing but motion, and make it work within that rigorous modern framework? How does it build on the legacy but avoid the pitfalls?
Exactly. It's about building. MT keeps the motion-only ontology. That's the core legacy. But it uses a field grammar, the mathematical language of fields physics already uses, because that language works. It matches experiment.
Yeah.
So nothing but motion becomes nothing but structured motion. And fields are just the very effective bookkeeping for describing that structure. They're not extra stuff.
Okay.
And we also reinterpret Larson's natural progression as default drift. MT sees this as a low-sync baseline expansion. Basically, regions where motion isn't very synchronized, where there isn't much structure, they tend to expand apart. That's the cosmic mean field drift. But locally, where coherence is high, meaning where there's lots of mass energy density convergence, which is gravity, takes over, motion becomes more synchronized, structures form and hold together. This keeps GR's successes, but gives it a motion-based story.
And what about redshift? Does MT still entertain other ideas besides expansion?
It keeps the standard expansion, absolutely. But it also considers that coherence loss contributions could play a role in some spectral features. Think about light traveling through thin plasma. You might get effects like dispersion or scattering that could mimic some redshift effects. But, and this is crucial, these effects have to be quantified. They have to respect the cosmic distance ladder. You need to calculate, how big is this effect? If it's tiny, say so. If you think it's significant in some situation, you need a specific prediction and a test. No hand-waving.
Numbers. Always back to the numbers.
Always. Which means AT definitely replaces the sort of derive without calculus vibe sometimes found in RS. We keep the conceptual clarity, the boldness, but not at the expense of mathematical rigor. The goal is always the shortest path to a falsifiable plot, a graph, a number, something you can actually test against reality.
Right. This is where the rubber meets the road, where Larson's big intuition gets subjected to modern scientific testing. And for you listening, this is how these ideas stop being just philosophy and become actual science through concrete, testable predictions. What are some examples?
Okay, take mass. The Larson-inspired idea in MT is that mass relates to locked rotational modes of motion. So, the test could be, take groups of particles, like hadrons, pre-register a coherence budget, a way to mathematically divide up their properties into rotational versus, say, vibrational parts. The prediction, this budget should let you accurately predict the mass, the centroid, of new particles discovered in that family within certain error bars. If a new particle shows up and its mass fits the pattern, great. If not, the model needs work.
Makes sense. What about on the cosmic scale?
There, the claim is, areas with low sync density, sparse regions, should follow the smooth Hubble expansion pretty closely. But dense regions, cosmic webs, should show extra motions, convergence offsets, or peculiar velocities that correlate with a calculable coherence index. You could derive this index from things we can measure, like gravitational lensing or galaxy clustering patterns. The test. Use one part of the sky to build the model, then see if it predicts the leftover scatter in the redshift-distance relation in a different held-out part of the sky better than standard models.
You can even test the photon idea in the lab, right? Photon as oscillatory motion?
Absolutely. The claim is photon energy is its oscillation frequency, reflecting coherence in a resonator, like a laser cavity. And the line width, how spread out its frequency, reflects energy leakage, substrate loss. The test? Measure the resonator's quality factor, Q, how well it stores energy. Then, show that a specific sync leak model predicts the line width better than simpler models across different setups. If it doesn't offer better predictive power, the specific model fails.
And even into chemistry.
Potentially the claim. Simple rotational descriptors, maybe inspired by RS, could predict trends in binding energies or selection rules for how small molecules absorb light. The test. Define these descriptors mathematically. Pre-register them. See if they add predictive power when modeling real molecular spectra compared to standard quantum chemistry methods, ab initio baselines. Test them on data they haven't seen before. If they don't improve predictions, they're not useful.
These are exactly the kinds of tests, taking that Larson spirit, that bold idea, and putting it on the line. Either the specific claim earns its keep or it gets retired. The data decides. So who exactly was this Dewey B. Larson, the man behind nothing but motion?
Yeah, it's interesting. He trained originally as an engineer, also worked as an accountant. He was in industry. And he wrote his big works, the trilogy, Nothing But Motion. The structure of the physical universe, the universe of motion, completely outside of academia.
A real outsider.
Totally. Self-taught in physics, very independent, maybe even stubborn. His writing is incredibly clear, which helped him create this really memorable way of talking about reality, his ontology. But being such an outsider also meant he was kind of isolated. He didn't have his ideas constantly challenged and sharpened by that crucible of hostile review you get in academia. And that's a lesson MT takes to heart. They keep the bold vision, the clarity. But you have to submit the ideas to hard tests, engage with the critics, show your math.
Okay, so wrapping up our deep dive today, we've journeyed through Dewey Larson's really audacious vision, nothing but motion. We've seen its surprising insights, where it hit limits compared to modern physics, and crucially, how motion theory tries to carry forward that core intuition, but with the full rigor of modern science. It's quite a story.
Yeah, I think motion theory's message to Larson, respectfully, would be something like, your core axiom, nothing but motion. That's our axiom too. We're with you there. Your natural progression. We see that as our low-sync baseline expansion. Your gravitation, that's our convergence, where motion gets more coherent. We see the connections. But, MT would add, we can't just discard the math, the vector calculus, the field theory that demonstrably works in the lab. We have to reinterpret it, give it a motion-based meaning, not replace it wholesale. And every elegant idea, every sentence, it must ultimately lead to a pre-registered plot, a testable prediction. That, you might say, is how motion pays its bills in the currency of science.
Beautifully put. So we'll leave you with this to think about. What if the universe really is just motion, and everything we currently talk about, particles, fields, forces, what if that's just our incredibly useful, but maybe incomplete, system for bookkeeping, all that motion? If that were true, what have we been missing all this time by focusing so much on the things instead of the flow? How might looking at reality as pure motion change how you see, well, everything? Yourself, the world around you. Something to mull over.